Thank you very much for the invitation. This talk is about a paper that I recently put out with one of the postdocs here, Carlos Corona, and my student, Zhongxun Cai. Well, I mean, the title of the paper is actually not this. It's not does all holographic systems have a string theory limit? But it turns out that the questions that we were asking is actually have a relevant statement to this question. So let me start out with the question that we were actually interested in. And the question, which is how I'll start this talk, is we want to think about the interaction of infinite number of massive higher spin particles. And we want in flat space, and we want to ask what does unitarity impose, or what precise constraint that is imposed, either on the spectrum or on the interaction itself. And you may ask, why would I be interested in this question? Well, there's various scenarios where such system obviously appears. For example, if you want to think about a large Yang-Mills theory, then obviously the question you want to solve is the meson spectrum. And at large n limit, the mesons are all stable particles because the decay rate is expressed by 1 over n. And therefore, you have essentially have an infinite number of stable particles with ever higher spins. So you would be curious about what that spectrum would look like. And furthermore, for any perturbative completion of a massless effective field theory involving a 3-point vertex, you can prove that by effective field theory, I mean that the theory actually contains higher dimension operators. You can prove that the perturbative completion has to contain an infinite number of massive higher spin particles. So that scenario is relevant. And finally, in the context of ADS-CFT, where basically the statement is that the correlation function of the boundary is computed through Witten diagrams or interactions in the bulk, in the flat space limit, this picture essentially just becomes an infinite number of particles with ever higher spin corresponding to the primary operators of the CFT. And so there, you also have an infinite number of massive higher spin particles interacting. So there's a lot of cases where such system arise, and we want to just ask, what are the general statements that you can add, and you can say about this kind of system? So the statement that we would like to make is about the high energy limit. So basically, if you consider the 4-point S matrix, and you consider the large center of mass energies, the Ricci limit, basically you can say that you can show that the 4-point function always have to have this universal form, where it has some function f of t. T and s is just a Mandelstam variable. And s to the some power j of t, where j of t is the Ricci trajectory. So f of t encodes the poles in the t channel. Now this Ricci trajectory, which will be the focus of my talk, encodes the spectrum of the theory. Essentially, once you know the function, this function j of t, you know the spectrum. Because whenever j of t is equals to some integer number, that tells you that is where one massive state is. So for example, if we just think about Yang-Mills and gravity, these are just simple theory. The content of your spectrum just contain one particle. That corresponds to jt equals to 1 or jt equals to 2. The Ricci trajectory is just a constant. Here, there's various different scenarios for what j of t could look like. If you're in a Higgs space, then your j of t will rise with t, but at a certain point it will turn around and fall down. As many of you know, for the confining phase, essentially it's just a linear rising j of t. In the Coulomb phase, which means your system is ionizing, and therefore for any increase of energy, you have a large number of states coming up, then this j of t is just exponentially rising here. So basically, if I can impose a constraint on my function j of t, then this would be a statement about what the spectrum would look like for theories involving the infinite number of higher spin particles. So this is what I want to look at. And in fact, just this summer, Zohar Komodowski and his collaborators were able to show that in certain regimes, this j of t must be linear. So the only ingredients they use is that they use the unitarity, where the way that you use is that this function m of st at any pole, the residue must take this form, where this is the pole and this is just some Legendre polynomial. And unitarity is telling you that this function must be multiplied by something that is positive. And this is all they actually need, of course, with some clever manipulation. And what they use is that if the function looks like this, near to resonance, that means that when s is smaller than m and bigger compared to bigger than m, this function must flip sign. And since it flips signs between any two poles, so that means that there must be at least one zero between the two poles. And furthermore, they can show that this JT function, which I told you encodes all the information of your spectrum. You can relate it to the number of zero minus the number of poles. So essentially, just by analytic property of your function, they showed that for the asymptotic radial limit, where it means s is much greater than t, much greater than 1, this function, and assuming that this function vanishes in the radial limit, JT must be linear. So they successfully showed, in other words, that this system in this region looks exactly string-like because it has a linear trajectory. So again, so nothing was assumed. All was assumed was a unitarity and an infinite number of higher spin particles. So in this talk, I would like to go in a different direction and think about this question in the context of CFTs, and not precisely ADS CFT because I'm not going to assume holography. So I'm just going to think about it from the context of CFT and make connection. So in CFT, the object that I will be looking at is so-called the Mellon amplitude. And that is that the CFT correlation function, there's a nice representation where you can represent it as an integral over some variable, which we'll call just the Mellon variable, and with some function here, m, of this variable, multiplied by gamma functions. And so all the relations between the distance of the CFT correlators are encoded in just this function. So if you write it in this form, and as we go along in my talk, you'll see why this form is very natural, and it's actually, in fact, it turns out to be extremely useful. But let's just say that I can write it in this form. Well, in principle, this is just, you can think of it as just this is the Mellon transform, but it's just a transform now. And so the conformal invariance essentially fixes what these variables should satisfy. So it fixes that, for example, delta I must be minus delta I, which is the dimension of your external operators. And when you sum over any indices, this delta ij must go to 0. And so you can see that this is very analogous to if you consider delta ij as the product of pi dot pj. And this is just a statement of momentum conservation. So in other words, this function here has a very, defined in terms of this Mellon variable, has very similar property to a function that is defined in S matrix. And this relation will become more and more closer as we go along in this talk. So just to make the analysis very simple, let's just consider the simplest case where you have four scalar operators. So if I have 4 scalar operators, I can scale out this dimension-dependent piece and just leave with a function that is written in terms of cross ratios, which are conformal invariant. In this representation, then this what I call reduced 4-point correlator can be written because this is just 4-point, and once you solve all the constraints, you can see that the Mellon representation is essentially just 2 variables, t and s. So your milling amplitude will be s and t, and this is what the gamma functions look like, and the cross ratio will appear in this combination. So already you see this ms of t here is a function of 2 variables, very similar to a 4-point interaction for a field theory amplitude. Now, what properties should this ms of t have? You can deduce what property it has by looking at what properties the 4-point correlation function should have. So many of you know that since this is a CFT, that means your 4-point correlation function can be written in an OPE representation, where you can write as a sum over so-called conformal blocks multiplied by 3-point OPE coefficients. And this gives you a complete representation. Since it's a CFT, it gives you a complete representation of the 4-point correlation function. You can look at the behavior of this conformal block, which are known for even dimensions analytically. And if you take the limit where one of the cross ratio goes to 0, where the other goes to 1, it has a very simple form. It has a form where it has u to the delta over 2, where delta, again, is the external dimension. And Cj here is just the Geigenbauer polynomial that often comes up in scattering processes. And, for example, in 4 dimension, then this is just a Legendre polynomial, where essentially this is just your partial wave expansion polynomial. Okay, so comparing this with here, I've just rewritten down the Mellon representation. you can see that, so that for a given exchange operator with a given dimension and certain spin, it will correspond to a polynomial of this form that must appear. Now the Millen amplitude, the polynomial of u and v appears here with s and t, and since this is an integral over the imaginary axis, so that means we should really interpret this integral as picking up poles. And so this is telling you that the t and s must give this value for a certain exchange, and that implies that this MST must contain poles. So in other words, for example, this will imply that MST must contain pole for any operator is being exchanged at this position. So delta k minus jk plus 2n. So this is a rational, so this is the first information you gather, that this is a function of simple poles that have precise positions whenever there's an operator in your CFT spectrum. We also know that the CFTs satisfy crossing symmetry, which should translate into the reduced correlator having this property. Compared with the Millen amplitude representation of your reduced correlator, that implies that your Millen amplitude must satisfy MST equals MTS. In other words, of course, this must be an S matrix that is permutation invariant, so it has natural ST symmetry. So as you see, this is becoming more and more like really just an S matrix sitting inside a CFT correlator. Now, for the purpose of this talk, I'll make a certain assumption for my CFT. I'm going to assume that, so if you look at the Millen representation, you want to ask, why are these gamma functions sitting here? And of course, since I already told you that you should really interpret this integral as an integration of a counter integral picking up residues. Gamma functions have residues at 2 delta, t equals, for example, 2 delta plus 2n. That represents that these gamma functions are reproducing the contributions given by the double, like for the operators O, where in the internal you're exchanging two double O's with a certain number of derivatives. If in the language of if you have some gauge theory, if your CFT is a gauge theory, then these are double trace operators. But this is a generic statement. So these gamma functions are producing poles for the canonical dimension of this operator. But of course, we know that this operator will have anomalous dimension, and so that the anomalous dimension is being so the Millen amplitude is responsible for producing this anomalous dimension. And if you think about how anomalous dimension can appear in a diagrammatic way, you can see that it must come from, for example, exchange of two fields. Essentially, it looks like it's coming from a loop diagram. So since I'm interested in perturbative completion, so I'm going to assume that my CFT always has an expansion parameter such that the anomalous dimension of the double trace operator is perturbative. Okay, so that means I can just suppress this kind of diagram, which was necessary, to which this MST is responsible for producing. And in the generic ADS CFT language, that corresponds that you need a large hit. But here, I'm not assuming ADS CFT, so I'm just saying that there should be some parameter in my CFT where I can suppress the anomalous dimension of this kind of double operators. Okay, so let's assume that. Next, I'm going to assume that in the Ricci limit, where it means this function, I'm really treating this as an amplitude. And the s goes to infinity limit, this amplitude vanishes. I'm going to ask, what does this condition imply? But of course, you're going to say, why should I be interested? Well, why should I be able to assume this? Does any CFT actually satisfy this condition? If I'm assuming this, it better be that I can actually tell you when does the CFT actually has this behavior for the Millen amplitude. And in fact, we can say precisely when does this happen. So if I look back at my Millen amplitude representation, so this has been flashed over and over again, so I hope that it's increased the familiarity. Now I'm going to look explicitly at one of the residues that is in this gamma function, which is s equals to 2 delta and t equals to 2 delta plus 2n. So the residue of this integral takes this form. So as you see, since the argument is 2 delta and 2 delta plus 2n, I can have, as n goes to infinity, n much larger than delta, this is actually probing the Ricci limit of my Millen amplitude. So in other words, if I take n greater than 1, and I can use the fact that this is permutation invariant, this contribution is exactly corresponds to the Ricci limit of your Millen amplitude. And what does this limit correspond to? Again, you can just map, you can just look at the exponent of this cross ratio and you can identify what is this contribution corresponds to. And this contribution corresponds to actually the exchange of a double trace operator, as we mentioned before. So let's assume that MST behaves as S to the N. Okay, so if this behaves as S to the A, a large spin, then this tells you that this predicts that the 3-point coefficient will depend on spin N as N to the delta plus A plus 1 over 2. Okay, so all you have to do is, for your CFD, any CFD that you're interested in, you want to ask if its Millen amplitude will have a vanishing limit. You just have to look at the coefficient of your 3-point function involving 2 derivatives and this, let me just call it double trace-like operator, because it doesn't necessarily have to have it in. And for example, you can compare to the free theory. You can compute the free theory and even images. The 3-point function for the free theory takes this form. This has been computed long ago by Wojcinski and his collaborators. And you take the large n limit, you see that here, and again, just to remind you, n is spin. Then you see that the larger limit of your free theory, the 3-point function, takes the form of n delta minus 2/3. If you compare with the prediction coming from the Millen amplitude, that tells you that the Millen amplitude for the free theory, you can read it off. It's this s to the delta minus 2. Okay, so this is consistent. So essentially, we're giving you a prescription for looking at for any CFD. You can see what the Millen amplitude of that CFD corresponds to. And here you already see that it is consistent with the linear stringy trajectory because it's telling you that S is behaving as delta minus 2, where if you remember that delta is proportional to T because I'm taking that specific residue. So indeed, you can see that this free theory has a limit of its Millen amplitude where it actually behaves string-like. And this also tells you for the usual ADS-CFD, when the Millen amplitude vanishes, it vanishes when you're essentially in the small to hub coupling. Okay, so we're going to assume that the Millen amplitude vanishes, but here I've already given you a criteria to actually see whether your CFD has a region that satisfies this or not. Now, if the Millen amplitude vanishes, so what? What interesting thing will happen? Well, what will happen, interestingly, is that if this is vanishing as S goes to infinity for some T star, if you observe what the gamma function is behaving, gamma function is appearing as S to the T. So, in other words, for positive T, this gamma function is actually growing. So, in other words, you have a decreasing function multiplied by another function, which is actually increasing in S. That implies that you must have a saddle point. Okay, and of course, there's a question about whether or not when this vanishes, whether or not T star is negative or positive. But in either case, you can show that you can define it in such a way that a saddle point exists. So, I'm going to use this fact that it has a saddle point. Now, furthermore, I'm going to take the flat space limit that actually corresponds to the flat space limit S matrix. What does that mean? Well, what that means is I'm going to take the CFT, I'm going to take the scaling dimension of each operator to be infinite, while keeping the ratio of the different operators fixed. Why is this called the flat space limit? Well, if you look at from the conventional ADS-CFD point of view, if you compute Witten diagrams, you'll see that the delta is related to R times the mass, where R is the ADS radius. So delta going to infinity with the ratio fixed corresponds to R taking infinity. That's why this is usually called the flat space S matrix. But more importantly, taking this limit actually has another feature, which if you remember that whenever you're doing an OPE expansion, the OPE, you have the primaries and you have descendants. Now, of course, the descendants will all have their dimensions, which are integer or these space. And when you're taking this limit large, essentially you're doing an integral over all the descendants. You can show that essentially the descendants all collapse into a single particle in your spectrum. Where, for example, for scalar exchanges, the mass of that single particle is given by this formula. Okay, so in other words, taking this flat space limit, all of your poles in your S matrix now becomes poles of just the primaries. So I will show that the fact that, as I said before, that there's a saddle point that must appear in the S integral implies that my ridging trajectory will be linear. Okay, in other words, that my theory will be string-like. So I'm going to prove this. Actually, how much time do I have? Okay. So I can prove it real fast. So to show this, I'm going to probe the origin limit of my Millen amplitude through limits of the 4-point functions. I'm going to probe it in the other direction. And so the direction I want to do it is essentially the content of this claim. So the claim is that in the limit where one of the cross ratio is 1 and the other cross ratio is near 0, and taking the flat space with delta much greater than 1, this actually corresponds to the asymptotic origin limit of my Millen amplitude, meaning that S is greater than T is greater than 1. So in other words, just use the other slide. In other words, remember that I have my Millen amplitude here with some function. So I'm saying that take your 4-point correlation function. You push one of the cross ratios to 0 and one of the cross ratio to 1 and take the skinning dimensions to infinity. This integral will be dominated where this function, MST, is actually in the asymptotic region. That region will be dominant. How do I show that? Well, essentially what you do is just some simple application of the approximation for large arguments for gamma function. Since we're taking delta and S and T all to be large, then the gamma function essentially, you can use Stirling approximation, then it will be approximated into this form. Now, furthermore, since I'm looking at rigid limits, so I'm going to push S furthermore greater than T. In that approximation, so the integral essentially simplifies into this form here. So remember, I'm integrating along the imaginary axis. These T and S are all integrating along the imaginary axis. So if you look at this integral, for example, you see here, you have an S that is along the imaginary axis. That means that this is a highly oscillating phase here, essentially in the rigid limit where S is large. So in principle, this integral, for generic in U and V, the rigid limit is not dominant. In fact, the rigid limit is just not contributing to this integral because of this large oscillation phase. However, I'm not looking at a generic point for my 4-point correlation function. I'm looking at the point where V is near 1. So if you take V is near 1, you see that log V is near 0. So in other words, if you let S times log V to be much smaller than 1, that this rigid limit actually becomes dominant. So in other words, taking V equals to 1 actually corresponds to the rigid limit of the Millen amplitude. So instead of that limit being highly oscillating and canceling out, that limit actually becomes dominant in your contribution. So that's why I want to take this cross ratio to be equal to 1. And we still have U. But also, if you look at this piece over here, again, so the T integral is also integrating along the imaginary axis. So here, this is also a large oscillating phase. And since I'm taking T to be large, this will be in principle all be suppressed as well, unless using the same trick, this argument inside here is actually near 1. So in other words, this is highly oscillating for large T unless U, this cross ratio, is proportional to 2 delta minus T over S. Now remember, S is much greater than T delta minus T, so that means U is approaching 0. So this confirms my claim that if you take V equals 1 and U equals 0, this region is as I already mentioned, the region which we're considering S much greater than T, delta much greater than 1, this region will dominate this Millen integral representation. Now, claim 2. In the asymptotic region limit, the flat space amplitude, the rigid slope must be linear. So this is the thing that we're going to arrive at the conclusion for the bulk of the statement. In other words, in this region, it must be string-like. And how did I prove that? Well, remember that when we assume that MST start vanishing in the rigid limit, the gamma functions are growing, and therefore a saddle point must emerge. The fact that the saddle point exists in this limit must be consistent with when I'm looking at this other way, where I'm taking U and V towards certain limits. So I must see this saddle point appear. So in order to, to make contact with my flat space amplitude, I know that already in the earlier my talk, that I know in the flat space amplitude in the rigid limit, it's written as a function of f of t times s to the jt. So I can just insert this, since I already told you that in this u equals 0, v equals 1 limit, it's dominated by the rigid limit. So I can just replace this for my Millen amplitude. So I can write this down here for my Millen amplitude. And for the purpose of my analysis, now I'm going to analytically continue my contour near the real axis. I can do this, I can just twist this down to here because all the poles of my functions are all on the real axis. If you remember, the pole of the Miller integral corresponds to the dimension of your operator exchange, and obviously the dimension, even if it's anomalous, is always a real dimension. So that means that the poles are all on the real axis. So I'm free to rotate this down here. Good. So once I plug this into my Mellon amplitude integral form, then I will ask whether or not, what is the condition that the saddle point exists. Now, the only place, so I'm going to separate out the piece that depends on S, since we're saying that the saddle point must appear in the large S limit. So this H function, which depends on S, takes this form, this very simple form here. And taking the saddle point equation basically tells you that this function, this combination must be 0. Now, of course, we have this log V here, so you might say that this doesn't tell me anything because S is going to 0, and log V is also going to 0 because V is 1. Well, sorry, 1 over S is 0 because S is large and V is 1. But remember that we're really in the region where S times log V is much smaller than 1. So that means that this saddle point equation translates into T plus JT must be smaller than 1. So for the saddle point to exist, this equation must satisfy. But we already know that it exists. So the final ingredient is to remember that we're really looking at this equation in the large T limit. Okay, so you can think of JT as some arbitrary function of T, and that T plus JT must be always much smaller than 1. You can just think of it as 0. But T is large. So the only way that this equation can hold is if GT is linear with T, right? Because if GT is higher power than T, then this equation obviously cannot be satisfied because again, we're at large T. On the other hand, if GT is suppressed does not have this T power, then this also cannot be satisfied. So that this tells the fact that the saddle point equation looks like this and this equation must hold at large T tells you that JT must be linear T. Okay. So in other words, we proved that inside the CFT, inside the 4-point function where we have a Mellon amplitude, where you can interpret this Mellon amplitude in the flat space limit as the scattering of infinite number of massive higher spin particles. For this kind of system, JT in the asymptotic region limit, JT, your rigid trajectory has to be linear. What did I use? Well, actually, I already used unitarity because of the fact that I'm relating this to a 4-point function, and I'm assuming that this 4-point function for your CFT is already unitary. And so therefore, unitarity is actually used in my argument. Okay. So in conclusion, as I said in the beginning, any spectrum of interacting massive higher spin is encoded in this JT function of the 4-point function. And this statement in itself is very much like a CFT, because in the CFT you'll also say that the 4-point correlation function gives you all the information that you need about your theory. Now, using the Mellon representation of the 4-point correlator and properties of consistent higher point S matrix can be studied in the flat space limit. And so so in this analysis, we're essentially taking. Well, actually, we're not the first. Pedro Vieira they've also started in this direction, with using this correspondences to study flat space S matrix. But really, this is really initial steps towards this direction. And just using the very simple arguments to see why this is very powerful, we show that if you assume that the Mellon amplitude vanishes in the rigid limit, you can prove that JT must be linear. Your trajectory must be string-like. And it doesn't matter what spectrum, what degrees of freedom you have. If you impose unitarity on that degree of freedom, the trajectory that you get out must be linear and string-like, at least in this region. Of course, this doesn't prove that this doesn't show that it must be string, because string theory is a statement that JT has to be equal to T in all regions. So right now, we've only proven that JT is equal to T in the region when T is large. And when T is finite or T is small, we don't have a statement yet, but at least if T is large, asymptotically, it has to be string-like. Or translated in another way, that your spectrum, for any consistent spectrum, at the ultra-high energy limit must be integer space. That's another way of saying what the prediction is. It must be integer space at ultra-high energy. And finally, we have also made a statement, a prediction of when your CFT actually will have this behavior. First, actually, there's two criteria. One is, as I mentioned, these double operators that you're computing must have a perturbative parameter in able to separate the anomalous dimension. And second of all, you can look at your three-point function of your CFT, this three-point coefficient, and you look at particularly these three operators, and you look at its dependence on n, where n is the number of derivatives. And the prediction is that for any CFT, the n behavior of this function will behave as n to some delta plus a minus 1 over 2. This a information tells you whether or not your CFT actually will have a vanishing limit or not. So just looking at a three-point function, you can identify which CFT has any hope of having a string theory-like limit. I guess this will be the end of my talk. All right, thank you very much.
Okay. Question? Okay.
You're concerned about instinct.
Yes.
You have infinitely increasing trajectory.
Yes.
And eventually you may have something like Hagedorn temperature.
Yes.
And Hagedorn temperature does not conflict unitarity.
No, I mean, oh, by the way, here